Okay, fine. So we're thinking about something called correlation function, or more precisely, the target is the goal. This goal of this lecture is to compute this. So this is roughly speaking measurement probability. Find a pair of particles in position x1 and x2. That's the goal of the regression. And then, I mean, so this is the two particle density measure. And to compute this quantity, so we somehow use the so-called statistical model. Sometimes we do things. So to derive this and okay. And we'll work on ground canonical or some more. Yeah. So ground canonical. So last time somebody asked me, this is E to with appropriate normalization. In the box. And then, so we will work on canonical. Example. It's if we treat it as a Hamiltonian. And then if you use the Heisenberg picture, the Heisenberg picture, so what we need to do is that so to use Heisenberg picture, it can or better. You can find later. That's Heisenberg picture, and then And if you solve the hydrogen equation, you given by minus like this way, you get better, e to the plus there, q, plus how the time evolution of the momentum force dk is to behave under the thermal temperature calculation. So last time, we learned, so the rho is unnormalized one is e to the minus beta h, and this one is unitary operator p e plus I h e over h. So here the beta, then p is related by IP over H bar. So beta can be understood as an imaginary time. And, so this unnormalized density metric can be understood as an imaginary time evolution. Okay. And then let's call BD theorem. Sorry. So let's call this BD theorem for take on simplicity. For the take on simplicity, we call it BD theorem. For BD theorem, the statement of BD theorem is as follows. So the C check and C check. So these are operators. It's given by trace of. And this is canonical, just. And this one, so this is just definition. So in statistical mechanics, expectation value is always just put the operator with density matrix and take a trace. That's the definition of expectation value. And then this one is given by sigma p. Where P is a permutation matrix. So those are permutation matrix. Elementing permutation element. Permutation. Permutation group. And here we assume that the this dimension is assumed like a P1, for example P2 and so on. And Pi, P minus 1, so that's the assumption. Let's prove that. So let's prove that. So the computation relation Ci and Cj and sigma. So the sigma means that this Gaussian function can be understood as they both can be treated as a both parameter or boson. Of course, sigma is for boson what? Plus 1. And for fermions, we have a -1. Okay. So you can treat both. Okay. Okay, since it's really middle of the course, I think it's getting. You guys are doing homework, and I think most of you guys did homework on the homework. Getting tired, so but still we need to prepare to go to superconductivity. So you have to have a strong mind to catch up the content. Otherwise, still middle, improve. Long way to go. Okay, anyway, so let's do this computation ratio is given. I define this ij, and this is given by delta ij when the ci and the cj is theta qj minus sigma delta j and ci. Like this way. That's the standard computation relation we have for bosonic and Bravais mode. We impose, so this is what we learned from second quantization. Essentially, this is a restatement of second quantization. Okay. That's what we learned. So let's apply them. C1, C2, C2n is given by 1, 2 plus sigma C2, 1. This is a computation relation. And C3, C4, C2. Okay, that's fine. Okay, and then, so this is given by 1, 2, like this way, and then sigma C2 and 1, 3 plus sigma C1 4 up C2. Okay. And this can be understood as the 1, 2, C3 and plus sigma 1, 3. Because that's P number already. 1, 3 is P number, and then C2, C4, those C2. Okay, and then the rest is this guy, and then I keep going. Sigma 2n. So if you do that repeatedly, you can get like this way. Then E3 dot E2n minus 1. Okay, and the last term is and then last term is C to n minus 1. C2, C3, C2, and C. That's so you just move this C1 by just using computation relation to the right. Okay? That's what I did. So recursively. So this is 1, 3 commutation, that's 1, 4, then 1, 5, dot, dot, dot. At the end of the day, you hit the 1 C2n. The 1 C2n will give you this guy. And then at the end of the day, if you swap that, you will get this. Fine. So those are the constituents. Okay, let's look at the last element. Okay, so now I erase this today's call. Okay, let's do the step one by one. So recall that the C2 of C2 and C1 is trace e to the beta omega minus whatever Charlie h naught. So this is the h naught minus n. 刚刚上born just those n. First, in the case of the in the trace, you can bring this one into here. This is trace d1 e to the beta omega minus h naught, Charlie h naught e to the n. Okay, like this way. And then you can do the computation relation between these two. We know the Heisenberg from Heisenberg equations. What you get is that the distance is equal to so it is C1 and then e to the minus beta h naught h naught equal to e to the minus beta h naught C1 times the e to the minus beta is from 1. So that's the what you get from here. Okay. So, and then if you add the dagger, so from here, so okay, the right of it's a computation. Essentially, C1 and A, Charlie H naught is given by, so this D, DK, C1, DK. Therefore, if you use this one, you will get exactly this quantity. And then, oh, sorry. Oh, it is. Yeah. So therefore, so what you need to do, and if you add a dagger, if you have a plus sign, this becomes plus. Plus there is a 1. So therefore, I call it this quantity A1. And if you A1, you have A1 of layer rate of T3 minus beta omega with what? Omega something h naught C1, C2, C2. And this is Ader. Ader is I don't need A. You know it. Sorry. The Ader is the plus 1 for C1, minus 1 for C1 type. C1 type. Sorry. And then this one is equal to just expression from statement. So just plug this one into here. Okay. And the left hand side is equal to what's written here. Therefore, bring the right this guy into left hand side and just divide by overall part. Okay. So therefore, at the end, what we get is that the and so on. and then plus 1. Like this. Okay. And in particular, so this is A, sorry. And then n is equal to 1 case, this reduces to C1, C2, is equal to 1, 2, divided by 1 by sigma A1, A. So that's the key. Okay. So therefore, if you use this trick, we just keep plugging. So it's 2-point function. It can be understood as 2-point function. And plug back that back one into here. So therefore, you will get like this. Like this. I forgot to put the sigma. And then here you have the sigma. And then here you have the sigma. Okay. So that's what you get. And then you can do recursively. So, so we have a contraction of D1, D2, and what's left is the 2n minus 2 correlation function from the other two. And you can apply the same thing for here. And so, at the end of the day, so you will get this one. Did I? Oh, yeah. At the end of the day, you get this one. You understand? In zero case, no need to write that. Zero case. I hope it's on the panel. Fine. So the simplification of this relates to the following quantity, 1, 2, and the call. Okay, and then so here you can have a pairing between these two. You can have a pairing in two operators, either like this way, or you can have like this way. Okay, okay. And this can be understood as the so if you try to bring this guy, if you want to try to contract with psi dagger and psi, so you need to bring this guy twice. You need to shift twice. Therefore, you have sigma square of psi dagger x1, psi x1. This one plus sigma. This yellow one. this way. You know what is that? Okay. So therefore, so this can be understood as the this one. Last thing. So this sigma is at the if it is the fermion, so once you swap two operators, you get the negative one. And if you do that twice, you get the sigma squared, which is 1. But here, time matters. Hold on. Okay. So that's how you compute. And often, so this with contraction, for instance, if you have the schematic on this, if you have B1, C2, C3, C4. Okay, if you try to compute this one, so 1, 2, 3, you just contraction is like this way. Plus sigma 1, 2, 3, and 4. And then sigma square 1, 2, 3, 4 is something like this way. Those contractions is just contraction is like this way. It's presented by just drawing edges between two vertex. That's how you write down the deep contraction or deep contraction. And often this contraction means it's called width contraction. Okay. So both of these, so we consider this, so we try to apply this to this particle density method to the botonic phase. So both not sigma equals 1, and we write that this start of x is the expectation value and its fluctuation sum of CQ, and then phi q of the of q, where the psi of x expectation value is given by half of psi of x, not the condensate, the Einstein condensate wave function. You have so this is the average. And this is the calculation. So if you write some side like this way, then it's easy to see that the involved one and quantum is given by diagonal C starts with 1. I call it this one, fluctuation part of the college phi of X. And this can be written as sum of the Q dagger, the Q and the phi Q dagger and phi Q. So, what's written? And do you, or like this is star? And do you remember what this is about? CQ dagger and CQ. You remember? Yeah. So this is the number density operator and number density operator and at state Q. So that's right down. And if you plug this one into here, sorry, okay, so 2 bar density matrix. So roll of X3 is given by and sigma rho 1 X3 and then X1 and then the overall factor is like this. So this is just straightforward calculation. I just leave it to on an exercise. So if you shift the expectation value with fluctuation operator, you just separate 2 parts. So average expectation value plus fluctuation. From previous calculation, you have you need to shift by the expectation value. So that's what you need to what you need to pay attention. So it's like any question problem. Okay. Then with this preparation, I will apply this BD theorem and this differential function. This into the standard. So the explicit apply this online. This formula to ideal gas. So ideal gas. Here I consider the Lorentz correlation function, but it also apply to the here implicitly here. So because if you do the same computation for premium, you can just have the same have the same answer from the computation. So therefore, what we use is for both of the premium. And here we will consider the wave function or operator. Sorry, K alpha x prime is something like x prime and alpha prime, okay, and alpha. The alpha is a spin level, and K can be understood as the momentum, and if you do that, the conduction will be used. Okay. So this is the mode expansion of the operator phi, and plug this into the formula. And then so and also so this extension value capital psi x can be understood as the n zero divided by s plus 1. So s is the spin. So 0 for boson, scalar particle for perimeter, and B is the volume, and 0 is the particle number. For T equals to 0. So not the extension value of the operator. And then I plug this formula back into here, into the computation. So again, so this computation. So I can now erase this here. Okay, to plug this one into here, what you did as follows. So rho 1 of x1 and x2 is given by n0 to s plus 1 times b plus dot alpha t divided by b sum of k and then times nk. And this is given by so for ideal gas, we already knew that this number density operator is something like this one, ek x1 plus x2 divided by e to the beta ek plus mu and minus c. It's not number density operator. So, with the momentum k. Now, so here, I mean, the space and this sigma summation. So this summation we can approximate by so this part can be approximated by as follows: delta alpha 2 and dk dqk. Like this. So by summation, by replacing summation by integration, then we can perform some angular momentum integration. So this one, angular momentum integration is because of physics. Then E K R. So that's so here, so I just have it's an inner product as a vector, and then we can just have the x1. So this is x1 minus x2, and the k is something like this one, and then this is there. So that's so here R is the expression the absolute value of the relative vector between x and y. And this one, angular dependence integration can be formed easily between y with r and sin kr over here. So then plug back into here and perform the integration. Perform the integration. And so now for this is equal to 3, and 0 over 2s plus 1 times b plus delta alpha 1 alpha 2 divided by b, sum over k, and then e to the base is k over 3 minus sigma divided by 1 times I and r divided by 2. Okay, so that's the one particle density particle density matrix. And this part, this dimension, we can do the same trick as before. I think this part I didn't print it out, so I just need to go back and see how it would look like. Let me check. So this dimension can be approximated by so recall that the d of so this is the d of E is given by sum over k and then alpha delta epsilon minus epsilon k. Okay. And the manipulation the manipulation I'm going to omit, and this can be written as the following. Okay, yeah, I think this is so this D is some density operator, and then you can plug that one into here and perform the integration. If you use this relation, density relation, this can be written. So this part Suppose the alter of the Q by the appropriate normalized ES plus 1 divided by P minus infinity to infinity E epsilon E of divided by E to epsilon and sigma. And then now, so we use the epsilon k is the relation between k squared divided by 2m. And then, so this part can be written as under 2m is going over by h of maybe h of. And then same thing here. Okay, that's what we have. Fine. So that's the expression. And then we know that this density the density operator can have the following expression. So this is roughly 2s plus 1 e divided by 4 pi squared and m over h squared divided by c half is called half. And so that's what we derived last time. And then we can plug this one into here, and then okay, that's what we can plug that in. And if you do that, what you get is yes, and we need to change the variable. Okay. Okay. So if you change the, so as you recall, we have this average epsilon is equal to epsilon q, so you have a tilde version and for energy momentum variable, so the where epsilon q is given by h squared, k q squared, sorry, pi over L q squared divided by m, and the L q is given by E divided by n. Okay, so that's the tilde version, and if you rewrite everything in terms of the tilde version, so rho 1 of x1 and x2 can be written as follows. And 0 divided by x divided and 0 divided by h plus 1 and e plus delta of 1 of 2 divided by 2s plus 1 e capital N and pi over 4 and then 0 infinity e tilde was half so tilde minus 2 minus divided by 2 tilde minus sigma and then time k q r equals tilde over half and k q That's the integration. Kind of complicated, and then all those derivations long stored into short. I think I keep it right. So these all long lengthy calculation into short. So this one particle density matrix can be written as follows: S plus 1 by 5 and 0 plus n plus alpha 1 L alpha 1 where L this is the function function L of x is given by pi over 4 divided by theorem space means going to the sigma mean divided by 2 sigma sigma half k sorry x divided. So that's the function here. And if you consider this limiting behavior of L of x, so this behavior as follows. 1 minus n 0 divided by n, okay, and 0, where x goes to 0, and the x goes to infinity. What's how it behave? Like when x goes to 0, or x goes to infinity. Now, so this guy is behaving like n over es plus divided by e, x goes to 0, and 0, and x goes to infinity. That's what we have. Okay, so that's the case. So what's the meaning of this one? So if you look at this one, so x is what? X is the x1 minus x2. Okay? x1 minus x2. And so if you consider this one particle density matrix, x goes to 0 means x1 is equal to x2. When you set x1 equal to x2, this is essentially become like this, right? Okay? So this is essentially numbering operator, number density operator. Therefore, when x goes to 0, n over 2s plus divided by b. So which means that so system has a particle n particle volume b. Volume b, and then so this is n over b, the essential density matrix when if s is 0. But if you include the one half particle, you have a fusion minus 1. So you have yeah. So you have plus and minus 1. You can have a plus minus 1. So you have a fermion, you can have either plus or spin up or spin down. So you have to divide by this to get that number density up. So that's the physical meaning of this. So one particle density matrix essentially is the when x1 goes to x2, it becomes number density operator. And when x1 goes to x2 goes to far apart, it becomes 0, which means no correlation between them. You see? So if you have a fraction of x1, and you have here, and the diagonal of X2 and so on is that they just parabolic with no correction. Okay, so that's the really awesome. And then so this is one particle. So the dimension, roughly speaking, we can just compute. So Q of x1, x2, x1, x2 is equal to rho 1, x1, x2, rho x1, x1, rho 1, x2, x2, and plus sigma rho 1, x1, x2, rho 1, x2, x2. And with up to some constant shift, after constant shift. So this is not important, actually. And if you use this, plug this expression from rho 1 into here, you can just have the following expression for two particles. Then scale, which is the following. Over. So if you plug this expression into here, then just massage the formula becomes so this is the two particle density matrix. So let's look at what it means. The first one also is after 1 is not equal to alpha 2, spins are different. It becomes just 1. So the overall normalization is actually quite not important. So this part is important. So it becomes 1. And this means that there's no correlation between the different spin. So this is the I call it this one G alpha 2 of R. So this is always the G alpha 1 alpha 2 is equal to 1. Become so which means that there's no correlation. For different particles. Different speed particles. And then and then if you just consider that alpha 1 is equal to alpha 2 case. Okay, alpha 1 is alpha 2 case. So since there's a sigma here, the behavior significantly change between both of the fragments. So let me show that how this correlation function looks like numerically. Okay. Okay, so this is the behavior of G alpha of R. Okay. Okay, let's do it. So this is so let me ask. So the solid line and the dashed line are the either boson or fermion. So fermion is okay. So how about solid line? Solid line is either boson or fermion. Which one? Fermion. Why? Sigma is negative, sigma 1 minus negative, and most likely this is positive. So therefore, so the solid lines are fermionic. And then, as you can easily see, so G00 it becomes 0. Okay, G0. Sorry, when R is equal to 0, it becomes really 0. Okay, so therefore, this means that the because of Heisenberg principle, when you R equal to 0 means that there's a at the same state, same positions, there is the same spin appear. Okay? Same spin appear. So therefore, it has to be 0. The correlation needs to be 0 because you cannot have the same position in the term. So therefore, it just goes to drop to 0 at the origin, at the R equals to 0. Okay? And then when you take R goes to infinity, it just also approach to 1. So therefore, this means that so as I mentioned, so rho 2 is the probability that to find a pair of the particles appear in x1 and x2. Okay? Pair of particles that appear in x1 and x2. So this is x1 and this is x2, and you have a whatever. The same particle appear whatever. Anyway. Two pair of particles will appear in here. So appear in here. X1 and x2. But if you take this one, R goes to infinity, there become no correlation. That what it means. When you R goes to infinity, it becomes 1. So now let's take a look at the bosonic case. So bosonic case. So the important thing is that the most characteristic behavior is that the so when the R equals to 0, so above the typical temperature, it becomes 2. So this means that you have attractive forces between these two bosons, and then you can have the non-trivial wave function at even when R goes to 0. But once the temperature below drops below the critical temperature of the Bose-Einstein condensate, so this 2 is also becoming even origin becomes less and less, and then when t equals 0 becomes 1, everything becomes 1, which means that all those this part becomes 0. So L when t equals to infinity, 0. So L also becomes 0. L function of L. So it should be able to find Q. So mu equals to 0, this one equals to 0, and the T Q equals to 0, which means that this dominates. So this becomes infinity. Something divided by infinity becomes 0. So therefore, function L over there. Sorry. So when t equals to in 0, so this function becomes 0. This function becomes. So therefore, everything becomes the G alpha is becomes 0. 1. So this means that at any distance, there is no correlation between them. So therefore, the particle lose the identity. Each particle becomes identity, and they form the Bose-Einstein condensate wave. So that's what it means when the t goes to 0. So that's from the even correlation function. You can see the no correlation between particle and the speed of Bose-Einstein polysymetry. That's the what this calculation helps. Any questions? Okay, so that's the calculation of the reduced density matrix in the ideal case. Okay, so that before taking a break, I want to explain the plan for the course, due course. I think. So the following plan, so I'm going to talk about so-called from now green function. In the non-interactive system. And from there, and also I'm going to talk about, so that is some kind of, since we talk about this as the expectation value of operator, so it's very natural to discuss the green function of the non-interactive system. But I'm going to omit interactive system. So actually, this requires so-called Feynman technique, Feynman diagram technique, Feynman diagram technique. I mean, since some of you guys are taking the QFT courses, some of you will take the QFT course later. So I'm going to omit. Actually, I mean, this is also important to learn, but if I do talk about the green function or correlational function for a long time, I think it's going to be more like a QFT course. So, which I want to avoid. So I'm going to skip this part. I wrote the LaTeX, but I just commented down. So just this non-interactive system, I just talk about what the green function is about, and then I'm going to talk about lambda, Fermi, liquid, theory. So Landau's Fermi liquid theory is that the here you just consider fermion with interaction. With interaction. So it's no longer ideal gap. As I mentioned, the ideal gap, there's no interaction between particles. So that's the ideal gap. But however, even if you do interaction with some approximation of the effective field theory, if you use the effective field theory, it's almost like that. Pretty much behavior is the very similar to the ideal gas. Yeah. Especially when temperature is very especially temperature is very low. Equals to below that. T is very small. So that's what the lambda founded. All very similarly, there's some approximation is required, which is called Landau's parameter. So you need to add some parameter to the ideal gas form to describe the Fermi liquid. Okay, so that's the next thing, and then from there, after that, I'm going to talk about superconductivity. Yeah, so this is my Cook Cooper Hudson interaction or Cooper's attractional force, Cooper's and BCS theory, and so on. And the Meissner effect, whatever, blah, blah, blah. And also, at the end of the day, so I'm going to talk about this phase transition, so spontaneous symmetry breaking phase transition. That is a block. We think it's the number 6. I think 6 lecture today? I don't remember. Yeah, I think 6 lecture. Okay. 6 lecture. Okay. I think till the end, at least I use the 10. Hopefully, I can finish this one by 10 or 11. After that, I will talk about the I will talk about the spin, quantum spin system. So that's the plan. But if I'm not gonna rush, if I don't have so much time to quantum spin system, I'll be very just brief. I mean, the main thing is the superconductivity. So actually, that is the goal. So that's the plan of the lecture in due. Any questions at this moment? If not, maybe we can take like a 10 or 15 minutes break and then talk about this string function. Okay, let's take a break. And yeah, if you have a question, just let me know.
他讲那个长城是跟那个上面那个的后面就他们2点还有在后代这个2再往下降的那个我现在正好有一个这个目标，那就是这个理解啊。那还就是，反正他只用了他没有那个边际，就是要连续性的，就是不能不还说只不能超越这个所以基本上一个常数的关系。对，然后还对。 看着这边这个一定算是，我感觉它这个就是如果大一点的话，就是这极可能是啥？
大型就是它市场的那个页面无所谓。
我感觉就是那个战争播报，因为就是的，然后把观点就定义了。我真少。就是在某个页面一个，在某个位置上的那个播报展开，那个就在某个多色彩上面。两个情况，它是就把这个换成这个换成就这样。这那个一般是会，这一开始就是正开始，这是它的这个推灯，然后这个算是这个。哎，这我刚想，哎，就是把这个求到。一般的这个全到，一个例子，其实那我们现在的这个一个就是来，我看一个来的，这个我是因为做可能还真是就是求导时候出一个这种东西，然后这种东西就在他这种，他讲的一方面有那个过程。
这是哪一步？
对，我没听过。
他说每节课
那这个是这个只是一个步骤。我一下是为题，我觉得咱们说应该是就是好奇。就是第一个嘛，意思是就是这个里面是我加多一词，哎，我这个是这个形式结构，连接后，很重要是它后面这就是从那个那个啊，就是如果它是一个啊，这个写错了。就是如果前面是研究，后面是看一个那是以后。那然后这个，因为必须把第一个压加位置，换位置，对，压加位置，谁不？第二个位置就这压出来对象和对应的。一点不行，一不是有国外性。哦，对吧？说对了，我记得很快。就是你发觉这个那个几个跟相对来说些对应关系。它相对是这样。
可以去转，可以转，
对能随便，
不能随便，但是整体都按照这个转。
然后这个东西类似于这一步，这个就类似于很对这个这是正常的，是。这个还没有别的，还没有别的我只会看。有人说4个测试没有3个这样就不见了。对，这个是我就是这个大概。2个例子，2个例子，还有这2个业务，还有就是商业。就是它这个 两组之间只有自己跟自己，要么就是两边相左。你说为什么等号能等不行？这个是常讲。就是那个配对的话，我应该是走就是一个产生这一个也确实是需要
纠结，
就是需要这样。
一个产生
然后这两个一个是没有的，因为这样是如果是两个产生或者是两个湮灭的话，这个是两个湮灭的话，你希望一个应该是。是如果你把这两配一起的话，就是应该是你，所以就是很难一点。对。
现在算了。
就是一个
对要比较。
Okay, so now we are going to talk about the green function. Okay, so since we already knew that if you use the decimeters, we can compute the certain value of operator. Using that property, we will consider the green function in statistical mechanics. I mean, the computation which can be do partially in the QFT, but we derive it in the statistical mechanics way. Any kind of conclusion can be obtained by using QFT method, so-called library. Time propagator and so on, but I'm not going to use that word. Everything is in terms of statistical mechanical one. The green function is what? Is the G method? So these are beta always the meaning of spin variable. And it's essentially the 2-point function. And then here it's called time order. Time ordering is so of course the exclusion value operator is always trace of e to minus beta. H naught minus mu n and offering. So that this is assumed. With a proper normalization, use the T cannot. This is the extension value. We validate this, and in particular, so this quantity becomes very important in the any statistical system. So we would deal with this, consider this one. And here it's H means high level picture. Namely, the size plus H offered. Like this one. This one. This is the coloring picture. Sorry. Sorry. In later. So in later it becomes like this, but at this moment maybe we can just deal with it as the so this is okay. Let me define like this. H star H output RT is the Euclidean time or this is the Lorentzian time. And OET like this. Here, change the notation. I mean, you can put H1 if you want. If you want H1, if you want. But for the sake of brevity, I'm going to omit H1. So the bottom one is Euclidean time. Or every so imaginary time. Or imaginary time. What's relevant in statistical mechanics is the bottom one. But still, we can just take a look at the. We can still take a look at the. Take a look at the Lorentzian time, and this time ordering is assumed as follows. Time ordering of T plus like this. Okay. So so if P is greater than P prime, you need to consider here. Okay? And so ordering is the how to say the so this is the T has to be greater than T prime. So this is more like the the future of the future and the past. The opposite. If t prime is the greater than t, you have to consider here. And now you have to swap sign dagger. Because t is smaller than t prime, so you have to put the smaller operator to the right and bigger operator to the left. But now when you flip it, you have to have the sign issue. So most likely, I think I need to write it down like this. The introduction of minus, I wrote minus in the program. Bottom is and the alpha beta is only relevant for scheme one part. Let's spend time open. This is the time open. Okay. And so this green function, so this is called green function G, and this can be understood as the if the left case you consider the particle created by t prime and another by t. So this is the r prime and t prime and the r and t. And here the particle value is created and the particle another class. On the other hand, if you are the so this is the t is greater than so here the particle is analyzed RT and created by R prime. So this is an analyzation. This creation. So this is the number and the time is something like this. Okay, so like this. Fine. So that's one way of considering the meaning of the correlation function. Yes, or more like a probability. So that appears this is that. So this is the here creation and then annihilation. In the left and the right is the opposite. And moreover, so when R prime becomes out and T, if you need T prime, then it's more like the green function is reducing to the expectation value of the diagram R and down R. This is more like the particle number density operator. So this is number density operator. Expectation value number density operator or whatever. Okay. That's the quantity for green function. And then you can consider if you apply the delta t, equal to 0, h equal to 1, and g. Okay, high temperature. Okay, I would erase H. I don't like H. So. One second. Okay, so let's apply the delta T in this expression. Delta T can see. So delta T can see this guy or this guy or this guy. Okay. So therefore, so if you apply this operator, the thing operator, you get that this guy. On the other hand, if you apply this guy, you get the second line. In the third line, you just apply here, you get this. Okay. Okay. And then, so this is equal to, and then if you apply Hartley picture for this one, is equal to, if you apply a Hartley picture, so this is equal to, so recall that so delta T, if psi hat is equal to essentially minus I times this part, and then psi hat. So that's what you get. This time issue I is somehow I mean something no, I think it should be okay. It should be high. And this 0 plus is like this. And also, we can use this, the computation relation between psi and psi dagger, R and R prime plus minus sigma is equal to delta R minus R prime. That's what you get from computation relation of the operator. And of course, you have alpha and beta and alpha beta. So we can use this too. So if you first apply the delta T here, you get the this term. And then from this computation relation between psi and psi dagger, you get the delta function. delta function. Is it okay? Is it okay? So therefore, so this is Schrödinger operator. Schrödinger operator acts on psi, you get the delta function. Not psi. Green function. This is the green function. The Schrödinger operator green function, you get the delta function. So that's the of full circle. Okay. So this is the So the Schrödinger operator acts on green function is the delta function essentially. Like this way. This is always like the same in any free field green function. So if you learn the QFT, this Schrödinger operator is replaced by Klein-Gordon equation. It can be replaced by Dirac equation. And the operator acts on green function. You should get the delta function. It's the same thing. Here I use just a non-relativistic system, so you shouldn't operate enough. But if you go to the relativistic system, you just change the Schrödinger operator. Replace it by replace it by triangle. This is the defining equation green function. Okay. And then okay, so then what you need to do is update and this G operator RT so this can be, this guy is e to the minus h minus mu n and times t psi e to the minus I h minus mu n and t, and this guy is the e to the I h minus mu n t prime and psi h psi beta and e minus I t prime. Okay, t prime. Okay, so then the last one, instead of trace, last one can just bring it to here. Okay? Last one you can bring it to here. And if you massage it, you can get the minus I over t trace of e to the minus beta is minus. P prime, failure, and the alpha. So this is the other expression. I mean, here you just have a P minus T prime, how to say, time translation operator, which just move this operator into this in the same timeline, in the same timeline, and okay, maybe like this one, and timeline, and you just consider the correlation function between the same thing here. You just use a time translation from here to here, and then consider correlation function at the same time. Any question at the moment? Okay, and thank you. Okay. Hey, it's often useful to go to momentum instead of so it's often, so this is the, I express in terms of the, coordinate presentation, but it's often useful to present the momentum state. So the goal is to express the momentum state. Okay. Okay, so then we have and this one can be written as follows. Minus I P minus P prime, which is over there, and just express it in terms of all the model expansion. If you use the model expansion, we will get as follows. I think I need something. So here I just use the faculty of psi. Yeah, psi hat H offer RT can be understood with square root P, sum of K, E to the I K R, right? is from F and meaning T and D check K. D check K all. And recall that strictly speaking, I need to put the K and K prime here. But if you recall that this dk, what was dk prime beta dagger is equal to delta alpha beta delta kk prime, and then you have 1 minus f. F is T. So F is going to just I think I should call M. I don't remember. So it should be one of the whole small factors. E to J is from mu plus 1. Like this. So this is a whole small factor. Oh, sorry. So this is the so is this Fermi distribution or both distribution? Fermi, right? This is the plus. So I somehow use Fermi. Or if you want, I mean, I can put the sigma, and here I can put the minus sigma. So that's both can be applied both Fermi and both. Okay. And then here you can have ck prime beta dagger, ck alpha is the same thing. Thank you. This is a both or Fermi distribution. Because I mean, you know this P and C dagger is the number density operator, right? Number density operator. It's the same thing. It's a Fourier transformation of this guy. Fourier transformation of this guy. Okay. That's we already derived. And strictly speaking, you have to have a sum of a k and a k prime and massage the formula. But since we have a delta k k prime, I just omit this problem. And strictly speaking, everything k prime, and then you have multiply k r and minus k prime r prime. So which is, if we have a delta k k prime, I just omit this problem. Okay. So that's the case. We're just doing Fourier transformation. And then now, so we use some magic formula for that function to go to the momentum space. Okay. So I just want to, so it's already more like a Fourier transformation form of Fourier transformation. And then, so T minus P prime, the magic formula. Okay, it's positive, but very. So this is the form of the function, and plug that way to here. And so therefore, sorry, so I use this one for model expansion, and this is Fermi distribution, and here is the think and plug this one into here, everything into here. What you get is as follows. So this green function g is equal to delta of the beta okay. One minus f of k. like this. Okay, okay. Is it okay? Here I shift. Is it okay? So since in the present of e to the minus I, it's okay minus mu blah 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 blah. So it's better to shift omega from this variable to this variable. You understand? For upper one or lower one, lower form, we do the same shift by omega. Omega shift. But now, so the sign changes differently. Actually, I need to put something similar around here. Minus thing. Move to here. This is a formula. Okay, so this is exactly the Fourier transformation. So omega is a time moment, the energy transformation k is a momentum. So this is Fourier transformation. So therefore, we can have this guy. We can mention this guy. It's a momentum. The alpha layer. It used to be this one is the T alpha beta over RT half time theta. And if you do the Fourier transformation, you could and if you consider sigma is equal to -1, and that equals to 0, then we have the f of epsilon. K is exactly something like this thing. It's on 30, and this is 1, like this thing. So therefore, if you go to the, sorry, I think I changed, I think my H bar, so it should be okay. I set the H bar to be 1, yeah. So, sorry, my notation with since the delta is better. Sorry, delta is better. Sorry. Yeah, because I don't like the H bar, so I now, yeah, H bar to be 1. But now, so in the case of the fermion at the temperature 0, what you have is the following. Okay. When K, or maybe, yeah. Okay, when K is less than K fermi, F is 1. So therefore, this term you can ignore. 1 minus 1 is 0. And this is dominant. And then that case you have a minus sign. Because K minus Kf is negative. So this is okay. When K is greater than Kf, F is 0. So this F is 0. Therefore, you can ignore this term. And then here you become 1 over this one, which is the, you can inform with that. when sigma is good marginal form and sigma is good. Sigma is good. Okay. And if you look at this one, so you can see that the omega has the pole. Point. Namely, if you have sorry, somehow my figure is not straight. So there's a pole at the lower half plane. Yeah, this is minus when. Sorry, I got confused. So this one is the k is less than k, and this one is k is greater than k. Am I correct? Yes. Yes. So it's over. It's over. Okay. So all is a question here and here. So this means that there is a particle with energy with EK or ground chemical energy EK minus mu at when K is greater than K, you can have pole here. So this pole is a meaning of the corresponding particle. The choice of type of delta is the somehow corresponds to the total of this question. Okay. What the meaning of the meaning about the correction in momentum space. Any questions at this moment? Okay, well, we can consider the statistical mechanics of the okay, so the meaning of this one is kind of okay. Let me talk about a bit more the meaning of this one. So I used to mention here. So this green function is just so delta t plus some green function, you get delta function. And if you do the Fourier transformation of this one, if you do a Fourier transform of this one, so this guy will give you e to the k, essentially. So e to the k minus mu acts on g alpha beta k and omega is equal to, and then blah blah blah. So this is essentially, this one is the whatever e k upper normality pi to the power, and the q and the omega divided by 2 pi, and then e to the blah blah blah, e to the I k, or that's r minus r prime, and plus minus whatever I e k minus mu and e minus t prime. So this is a Fourier transformation of this part. And it is the Schrödinger operator really see the derivative just acts on here. Is equal to the same thing. So the same measure, you have an e to blah 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 blah, because it's just the function, right? It's just x minus x prime is equal to 0. It's exactly, you get this. But how? So this one, the moment of phase is equal to 1. So therefore, which means g alpha beta is essentially 1 over epsilon k minus mu, which is just over there. Sorry, I somehow missed omega. I should put the omega here, yes, yeah, omega here, and then minus, like this. Sorry. I put that. Omega minus epsilon k plus mu. Essentially. So omega comes from t, epsilon k is essentially whatever, k squared over divided by 2 essentially. Okay, so that's the minus BR. Yeah, if you have a potential. Is it okay? Essentially, if you add this along the Fourier mode, you get distance, which is equal to 1. I mean, delta function, if you look at delta function, Fourier transformation, you have essentially the same form of measure here, and then the same form of here, epsilon here, and multiplied by 1. So this part has to be 1. Therefore, essentially what you get is 1 over this. And this prescription delta, I delta sign is essentially coming from somehow forecast structure. Which you learn in QFT course more in detail, but I'm not going to go into detail. Okay. Any question at this moment? And we do the same exercise for the final temperature system growth function. So here, always I do the Lorentzian signature. We did the same exercise for imaginary time. Okay. So final temperature. Question. Okay. So the last time I mentioned this for trace of the partition function is essentially trace of row cut anomaly. As far as remember? Yeah. And then, so this can be understood as the cylindrical partition function. Or maybe you can write down time in the vertical vector like this way, and then the circumference in phase is given by like this way. And then this is the imaginary time. imaginary time. So that's what we learned last time. Can be treated as okay. And then we will do the same thing. So the instead of like psi hat h after r and then not p tau is essentially e to the tau whatever epsilon k minus or h minus mu n. And psi alpha r e minus tau h minus mu n. Now there is no I here. There is no I here. So it can be greater than the imaginary term. Okay, and if you do that, so what's going to happen? Then consider the same thing for the integration function p alpha beta. Is the time e sin alpha or tau sin alpha beta, and then on time alpha. So this is equal to the same thing. Going from e to the beta to h minus mu n. And essentially what we have is e to the tau, h minus mu h and tau minus tau prime, and then sin alpha r and e to the h minus mu n tau minus tau prime and there. Do you agree with that? Is it okay? But now, so we can solve this one. Oh, sorry, this is sin beta common and then alpha. Okay. And if you use this one start, so this one is equal to, right? And just absorb this one into here, plus beta. Okay? And then what I want to do is what? Bring this one into here. And then bring this one into here. So what you get is e minus h minus mu and let me write that e to the minus h minus mu and ultimate by prime by beta squared of prime, okay? And e to the h minus mu and tau minus tau prime plus beta and alpha equals alpha. Okay? Okay, and then I just want to write down manipulate beta and plus beta, and then you get e to beta h minus mu n, right? And then if you do the rotation again, this is equal to this is c alpha beta stage r and alpha prime, and then alpha is alpha. Okay? this is G alpha beta, R and R prime, tau minus tau prime plus beta. Okay. So even if you shift by beta, it doesn't matter. Because now this the I did. So this unknown decimetrics or weight or whatever probability grand canonical ensemble, there's no I here. And also this Hamiltonian translation, imaginary time, there's no I here. You can just combine them together to do manipulation. Okay. Okay. So this is exactly the same as here. Same as here. If you have R here, R T tau, and R prime and R prime, okay, you consider the correlation function between these two. But even if you shift by beta, you just come back original point. You understand? You just shift by rotation by beta, it's just rotation by 2 pi is the same thing. It doesn't change the position. And again, it's better to consider the moment. Okay. So now we can think about the momentum space. Again, we go to the look to momentum. And move to momentum space. We do have we do the pointing G alpha beta R and R prime and I times omega n, which is what we have. Minus beta and beta E times omega n tau G alpha beta and X prime, I'm sorry, R and R prime and tau. Okay, now omega n is constant because of the omega is constant because of the time circle is finite length. So omega n has to be something like a 2 pi n divided by length. Or presents 2 measure. And I explained that the n has to be odd for Fermat and then even for Bolton, which I'm going to explain from now. Sorry, I did something. Here. You need to be careful about those. You need to be careful about the ordering. I think it's not simply G alpha beta, there's time issue up here. it should be plus minus and oh actually it should be sigma. Where does sigma come from? Where does the yeah, I think somehow you need to swap that out. Let me think. Yeah, so this is essentially this is beta dagger R prime and beta plus alpha and then alpha of R. And you need to swap between these two to get the original one. So this is essentially sine beta dagger R prime. R prime and alpha. And this is sine alpha R. The original one is like this. And then you need to swap the order, so therefore you have a state. So this means that they want to do a beta rotation. For boson, you just have a periodic boundary condition. You assume periodic boundary condition. However, for fermion, if you apply the beta time translation, you get the anti-periodic identification. So you need you need time. So which means that you have to import anti-periodic boundary condition. Okay. So therefore, so this is the end result for fermion. And it's even for water. So for this time frequency, so time frequency, sometimes for mass balance frequency, for time frequency, imaginary time frequency, it's just the same thing. For n, it has to be odd because I mean there's a sign issue, so the minus sign you need to get. So therefore, the n has to be odd for fermion, so n has to be even for so that's the difference. Or I'm not saying something stupid. Yeah, I think it's okay. Yeah. Okay. Okay, let's apply this rule to the Fourier integral. So Fourier integral. Okay. So if you apply this rule, so this Fourier transformation has the following form. Unfortunately, 10 minutes is left. If you decompose from minus beta to beta, and this becomes 1/2 minus beta to 0, and then e to the blah blah blah, and e power plus 1/2 0 to beta, and the same e to the half. Okay. Now put this one from half, the same thing up here, minus beta 0, and then so if you have a minus beta to 0, so what's going to happen is as follows. So you have the e to the I omega n tau is something like a, so this is the tau, and, say the real part of the e to the I omega n tau, then this is the value. It has to be 1 here, but then you just go to minus over premium. So this is premium. Is it okay? Is it okay? And it's all right. So if you have the e to omega n beta, you should get the minus 1, right? On the other hand, on the other for monos, something more like this way. Like this way, it has to come back to 1. Is it okay? Yes. Is it okay? So because of that, if you swap the 0 to minus beta, you can just swap different folds. 1/2 1 minus plus e to minus omega n beta, and then 0 beta e to the I omega n tau, and then g alpha beta r and r prime and tau, and d tau. What was going to happen? So from minus beta to beta to 0 is replaced by 0 to beta by just adding this part. So this can be done because of this property. Okay. Okay, and essentially this one is equal to minus 1 to the n. So alpha 1 is the premium, and the bottom one. Yes, sorry, no, I mean, plus sigma, or sigma. Anyway, so that essentially this is equal to 2. Therefore, this is 0 beta e to the I omega n tau, g alpha beta, r and r prime, and tau and d. Fine. Okay. Okay, now do the same exercise for as before. So this is the case, and then next left. And if you do the same exercise as before, I'm going to erase it. So G alpha beta is essentially what you get is delta alpha beta divided by B from over K e to the I K alpha I of tau. and then sorry, R minus R1, and then minus from K minus and tau, and theta tau, and then the same model is not using X from K, and theta minus tau in plus sigma, so that if you do more expansion, you get this. Again, it's the same thing. So you have a size equal to sum over K, whatever. CK and the E are in rubber. So this transformation will show up. And with a proper normalization and plug that with the original formula, they do the fruit massage, you get it. And now I plug this into here. But here, the time integral from 0 to beta, instead of minus beta to beta. Therefore, this part is irrelevant in the integration. This is minus part, right? So how, if it is negative, it contributes. But this integral, if you plug this one into here, this time does not contribute because 0 to beta is positive anyway. So just only consider for first term and do the integration. So G, K, I, omega, n is equal to minus 0 to beta d tau e to I omega n tau minus epsilon k minus mu tau and the 1 minus therefore epsilon. So this is the integral. And this is equal to minus e to e beta I omega n minus epsilon k plus mu minus 1 divided by I omega k like this way, and then this is equal to 1 over I omega n minus epsilon k plus mu. Third question. So here, important thing is we don't use this theta of whatever. E is equal to blah 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 d omega 2 pi, and then omega plus A e to the I omega. We don't use this one. We no longer use this one to get the formula. We don't use this one. Which previously for Latin symmetry. So here's I delta, so I delta. Yeah. So the previously for run signature we used this formula to get the I delta contribution. Okay. For Fourier transform. But here we don't use it because of the finite temperature from 0 to beta, and then we just if you plug it into here, you get only this coefficient. And then at the end of the day, you get this. But which is almost same as before because omega is replaced by I omega n. Okay. So here, because the time is transformed to imaginary time, so therefore it's just the cost of going from Lorentzian to Euclidean or imaginary time is just replaced the frequency of the time version of the omega n. Got it further. Okay, so that's also a Fourier transformation for the green function. It's very simple. Yeah. It's very simple and then next time I'm going to talk about the more property of green functions and move on to another permanent liquid here. Okay, so let's stop here, and then if you have a question, just feel free to ask me.